Hello, everyone. My name is Mandar. I'm a PhD candidate at the University of Bonn, and I would like to present to you today the results of the recent work I've done with my collaborators, Cristiano Pulciani in Bonn and Oliver Hahn in Vienna, on the EFT of LSS. Let me begin by pointing out that the universe that we live in seems to have a variety of structure on all scales. So on the very large scales, you have cosmic web filaments and nodes, and also empty regions, voids. Then if you zoom in a little bit, you have structure on smaller scales. And if you zoom in even further, you have galaxy clusters, galaxy groups, and also individual galaxies. So what it seems is the case is that there is a lot of structure on a variety of scales. To make this more concrete, we can talk about the wave numbers corresponding to these spatial scales. And towards the small wave number or large scale limit, you have the Hubble scale, which corresponds roughly to the size of the observable universe itself. On the large scale or small scale limit, you have the so-called nonlinear scale, KNL, which corresponds to the size of those structures whose overdensity exceeds unity, size of collapsed structures roughly. And so the theoretical models that we have proposed so far have tried to describe these two separate scales in an independent way almost. So you have perturbation theory in the small scale or large scale limit, where you describe everything in these fluid equations and then you solve them perturbatively. On the other hand, you have n-body simulations, which deal with the nonlinear scales really well. The issue is that both of them have important shortcomings. PT, for example, treats the dark matter fluid as pressureless and without viscosity, or pressureless perfect fluid, which obviously breaks down at shell crossing, where you have different streams of matter cross each other. And PT by construction allows inclusion of modes, or does include modes, which are larger than the nonlinear scale. And this is, of course, not correct because these modes are non-perturbative at late times. Then you have n-body simulations, which make the macroparticle assumption, so they're only approximate. And also they have a limited dynamic range in the sense that you cannot resolve the small scales and the very large scales simultaneously. So with this background in mind, if you're interested in an intermediate scale, K, which is just outside the reach of perturbation theory, or at least in a regime where PT is not so accurate, and then also so large that n-body simulations cannot resolve them very well, then there could be a way of combining the powers of these two so that you can extend the perturbative predictions to larger wave numbers. And that is precisely the motivation behind the effective field theory of large-scale structure, which was proposed by a series of papers in about a decade ago by Bauman, Carrasco, Senatore, Zaldariaga, and others. And the idea behind this is the motivation is exactly the same. So you address the shortcomings that perturbation theory makes and then extend its reach to larger wave numbers. The way it proceeds is the following. Since you would like these wave numbers bigger than k nonlinear to be cut out of the theory, you introduce a cutoff scale smaller than KNL so that everything beyond this is deleted. In our work, we will always use a sharp cutoff, which means that all modes larger than lambda are deleted in every field that we concern ourselves with. Then you solve the coarse-grained equations, which are the fluid equations that I will describe in a second. And then you still have some dependence on k, which is larger than lambda. And this dependence is encoded in these unknown coefficients, which are the Wilson coefficients of the theory. If you would like to extract cosmological parameters from this, that is done by estimating what these Wilson coefficients are, either from data or from simulations. So now with this setup in mind, EFTs broadly come in two flavors. You have the top-down case. In the top-down case, you assume that your small-scale physics is known. Now, to be very precise, the small-scale physics in our case is the Vlasov equation, which I will describe in a second. But we can approximate the small-scale physics with n-body simulations, which are, again, very accurate on small scales. And then you calculate the EFT coefficients from the small-scale theory. On the other hand, if you have a bottom-up approach, you say that you don't know what the small-scale physics is, but you can still extract the EFT coefficients by directly matching the observables to data. So for example, you match the power spectrum to something that you measure either in a simulation or in the real universe. So these two approaches are different in spirit, but in the end, they end up with EFT coefficients which should be comparable to each other. And that is precisely the motivation of what we have done, which should be out in an upcoming paper. And the idea is simple. find a very, very simple universe, a toy model, in which these two approaches can be compared to each other. And this toy model comes in the form of a Einstein-de Sitter universe with plane parallel initial conditions, which means that it is effectively one-dimensional. And we start with a long wavelength mode at the fundamental frequency. Then we add a short wavelength mode, which is at 11 times the fundamental frequency. And then you take the superposition of the two. So you have the long mode here, which represents roughly the large scale structures of the universe, which has smaller amplitudes. And then you have the short mode, which contains very large amplitudes, but it's on small scales. And then we follow the evolution of this linear over density into the nonlinear regime using an n-body simulation. This is provided to us by Oliver. It's called Cosmo Sim 1D. It's publicly available. And we call this simulation Sim 111, where 1 and 11, of course, represent the modes in the universe. Now, let me show you how the overdensity field evolves as a function of the scale factor, which is our time variable for the rest of the talk. And we see that these initial density peaks form halos, which undergo shell crossing at just the snapshot before this. And then within these halos, you form substructure. So you can start to see already here this substructure. And then eventually, you have a second set of shell crossings around 4.3 or so, and then the system tries to tend towards virialization. So that's the system we are dealing with. Now let me describe some of the theoretical underpinnings of the approaches. So the master equation for all of this is Vlasov. It's the equation that describes how the one particle phase space density, this object that describes the ensemble of dark matter particles, evolves in time. And what the equation says is that the total time derivative of this object is 0. The first step is the coarse graining with lambda. And what it does is it retains the form of the Vlasov equation, but converts all of the fields into long wavelength fields or coarse grained fields, which we indicate with the subscript L. Then, as you would do in SPT, you take momentum moments of this equation, and you end up with a system of equations which you stop at some order, let's say second order, and you solve them. And this is the familiar fluid system of equations. You start with the equation for mass conservation, which describes the evolution of the overdensity field and also contains a velocity dependence in this UL. Then you have the momentum conservation equation, which describes the time evolution of the velocity field. This is coupled to gravity via the gravitational potential, and also has an object which doesn't appear in SPT because we set it to 0. This is the effective stress of the fluid. And this object tau is of crucial importance to us. And I will describe in detail what goes on here. But just quickly, the gravitational potential is connected to the overdensity via the Poisson equation. And together, this system of 3 equations governs all we need to understand about the overdensity and velocity of this effective fluid. So now you take your system and you calculate what this stress tensor is. So if you derive these 3 equations from scratch, you end up with a very specific form for tau. And you see that tau actually decomposes into 2 parts. One is a kinetic part, which comes mainly from pressure terms. It's described here. For example, this object psi L is the velocity dispersion of this effective fluid. And rho L is the density, and UL, of course, again, is the velocity field. The gravitational part comes only from the gravitational potential and its nonlinear combinations. One thing to note here is that at late times, the stress, despite the fact that it is a combination of the long wavelength fields, it combines them non-linearly here and here, for instance. And at late times, you will have some contribution from small scale modes as well. So now you can measure the stress from the simulations because you have all of the involved fields. Then you can model it phenomenologically. And the model that has been used in the literature, and the one that we're going to use as well, is a decomposition into a background pressure term, and then linear order terms corresponding to the overdensity and the divergence of the velocity field. The coefficients of these 2 terms are namely the effective speed of sound, cs square, and then a viscosity coefficient, cv square. Again, if you recall, an ordinary fluid has no stress tensor, right? Or no stress, at least, in the SPT formulation. So now these cs square and cv square, we can measure them in our simulations. And in 1D, it turns out that the best way to do this is to combine the 2, because delta and theta are nearly degenerate. And so we describe mostly the combination C dot square. So now once you have the C square measured from the simulation, you can apply the correction onto the power spectrum. So at the level of the power spectrum, you get the EFT power as a combination of the SPT power and then a correction term. And this correction term goes in proportion to the linear power spectrum. I will describe in a second what this alpha C is, but just a quick word on the notation. SPT is standard perturbation theory. 4 here refers to the fact that we stop at 4th order in the overdensity. And then the T means that you are truncating the SPT. So you could do SPT with the linear overdensity that we've described, or as you should do in EFT, you truncate the initial overdensity. So you delete in the initial overdensity all modes which are larger than the cutoff scale. So now the correction term alpha C is an integral over the past C square measurements. So you measure C square at all times, you integrate over the past, and then you have a weighting function, which is this Green's function. This is obtained by combining the linearized versions of the mass and momentum conservation equations and then solving them. And in Einstein de Sitter, this takes a rather simple form. It's a combination of these two kernels. So now you have this entire setup. Let me bring back the two flavors that we've discussed before, the top-down and the bottom-up. So the top-down approach of performing these calculations would be to estimate C square from simulations because you know the underlying short-scale physics, and then calculate alpha C. We do this in two ways for the purposes of the talk. We take spatial correlations with tau, which we call the SC estimator, or we fit tau with delta and theta, which we call the F3P, or the 3-parameter fit. So this is where you have knowledge of the simulations, or you know the stress tensor of the simulations. In the bottom-up case, you can match the EFT and n-body power spectra directly and then get alpha C. In our construction, since we're interested only in the fundamental mode, we measure one number at each time, and therefore the bottom-up calculation is exact. So the idea is now to compare the top-down and the bottom-up and see if they agree. So now on to the results. The first thing I would like to show you is a first measurement of C square as a function of time. The assumption in the literature has been that C square evolves linearly with time, which we see to be true until the shell crossings occur, which are indicated by the vertical dashed lines. And when shell crossings occur, this linear behavior no longer holds, and you see a peak value and then a sharp decline. And this continues to decline until we stop the simulation, perhaps as the system tends towards virialization. And we see that both estimators are in good agreement with each other, apart from some deviations at late times in F3P. Then the same C square can be translated into an alpha C using the integral that we've shown before. And now here we finally compare the top-down and the bottom-up case. The quantity plotted is alpha C, but a dimensionless version of it as a function of time, again for the fundamental mode. And throughout the results, we've been using a sharp cutoff with a lambda of 3. The top-down estimator are the dashed lines, which are more or less overlapping with each other. And then the bottom-up is the solid line, which is this estimator where you directly match the power spectrum. And you see that both of them are in pretty good agreement with each other. As you will see at the power spectrum level, these differences are tiny. But the prediction which is made in the literature, where alpha C is assumed to be proportional to A square, this comes from an assumption on C square, of course. This holds until A of 3 or so, but then breaks down. But importantly, as I stress again, the top-down and the bottom-up approaches are in agreement with each other. This is best seen perhaps when you look directly at the power. And here we again concentrate only on the fundamental mode, and we show the nonlinear power, again dimensionless, as a function of time. The blue line is the n-body power, which is assumed to be the correct one in our setup. The SPT power, the truncated one, remember, is the dashed dotted line, and that introduces an error of about % level or slightly larger at A equal to 6. And we see that both the EFT estimators, F3P and SC, are correcting for this error very accurately. There is a small difference, but most of the error is gone. And both of them again are in excellent agreement with each other, and also with the top-down estimate, sorry, with the bottom-up estimate, which comes directly from matching the n-body. So you again see that the top down, which is the dashed line, and the bottom up, which is the dotted line, you can see here, are in great agreement. Finally, I would like to show you what happens if you change the separation between these two scales that we were talking about. So far, everything we've discussed has been regarding this simulation, Sim 111, where you have the fundamental mode and 11 times the fundamental mode. Now imagine that this mode doesn't exist, right? So that's the simulation Sim 1, where you have only the long wavelength mode. Then you start to introduce the short wavelength mode at a different scale, which is simulation 115. So you have the fundamental mode and 15 times the fundamental mode. And then you reduce the separation between these two modes. So you go from 1, which is like infinity, then you have 15, 11, and then 7. As you introduce these modes, you can see in the n-body power here that there is a suppression of power as you reduce the separation, which is explained by the mode coupling between the short scale mode and the long wavelength mode. SPT makes pretty good predictions in each case, which is the dashed line, until a equal to 3 or so, but then deviates quite significantly. And as expected, as you reduce the separation, SPT becomes worse and worse. Right? For example, at a equal to 6, the Sim17 error is larger than 5%. Now onto the right panel, where we show again the n-body in blue. Now, instead of SPT, we show the truncated SPT, TSPT. And you see here clearly the effect of the truncation, which is that all simulations are now in agreement. And this is because truncation deletes this short wavelength mode here. And so everything lies on top of Sim1. This introduces an error of, let's say, 4% or so for Sim17, for instance, and smaller errors if you increase the separation. And in each case, EFT makes very accurate predictions, and it doesn't matter what the separation is, the error is a fraction of a percent or so. And so we've shown that the predictions that the EFT makes is not only accurate at a specific separation, but is also robust to changes in separation of scales. And with that, let me summarize our three main results. The first is that we've made a measurement of C-square as a function of time. We show that it deviates from its linear evolution after shell crossing and follows a downward trajectory where it reduces to a value smaller than what it started with. Then the main result is that the bottom-up and the top-down estimators are in good agreement with each other, which provides a nice consistency check on the EFT of LSS. And then finally, that the EFT predictions are very robust to changes in the separation of scales. And let me leave you with this result. For a lot more detail, please refer to this upcoming paper. Thank you.